Greetings, Earth people, from the aliens that built the pyramids. They've sent me to teach you a little bit of science. Most everybody else was pretty busy taking over other planets and so on, so they've sent me. Here is our formula sheet, and I added this formula that we used a lot last time. We'll talk some more about that. And we'll look at that in more of a general sense as well, and add a couple formulas that look a whole lot like this one. Last time we were together, we talked about tension and compression. We noted that if you have some shape, and one of the shapes that we used was a bone, so sort of a cylinder shape. We approximated the cross section as spherical, or not as spherical, as round, circular. And we tried to speculate what are the things that affect how much this bone here is going to stretch, either if you, how much this bone will stretch. If you compress it, so push it down, maybe you jump off a high table and land. And in that case, the ground pushes up on your shin bone, and your thigh bone pushes down on your shin bone, because the thigh bone's connected to the shin bone, the hip bone's connected to the thigh bone, and so on. Or somebody tells you a funny joke, they're pulling your leg, so they're pulling on your leg, they're pulling on your calf, your lower leg, and then your upper leg is pulling on your lower leg. We decided, well, certainly the length of your leg to begin with is going to affect how much it stretches. If your leg is just a millimeter long, it's not going to stretch as much with a given pull as a leg that's a meter long. Certainly somebody pulling harder on your leg, telling a funnier joke, for example, that's going to stretch your leg out more. And if your leg bone is thicker, a larger cross-sectional area, so larger cross-sectional area, bigger number down here, it's not going to stretch as much. So a smaller cross-sectional area will stretch more. So if we increase the force, have a longer leg or shape to begin with, and decrease the cross-sectional area, those are all going to affect the leg length. They're all going to increase the leg length. If you are doing that for different substances, whether it's a bone, a metal, a steel rod, a copper rod, a piece of silk, so all these things here, bones, piece of silk, steel rod, I don't have copper rod on the list, here's aluminum, those are all going to stretch differently. Let's look at that in a more generic sense. There's something called Hooke's law. So Hooke's law describes the general relationship between the force acting on something and how much that something stretches. So if we go back to this here, we can see that increasing the force, as we talked about before, increases the stretch. So if we increase the force, we increase the stretch. That's what Hooke's law says. So as F increases, delta L increases. So down here, though, we've got three objects, all of them the same mass. So in this case, the weights here are equal. That means F is equal for all. But notice they stretch different amounts, and this is a pretty subtle difference. This is a diagram from our OpenStax physics book. The stretch is different. So in each case, this force increase, or there's a force and there's a stretch, but we have the same force and a greater stretch for different objects. Here we've got a thin nylon rope, here we've got a thicker nylon rope, and here we have, I believe it's aluminum. So that tells us that there is some proportionality constant right here as well. This is similar to Young's modulus, which we used in a previous video. And in fact, this is the more generic relationship right here. So anytime you have something that stretches in this pattern, where delta L is proportional to F, that object obeys Hooke's law. So that happens in this region right here. So notice that not all of the graph, though, obeys Hooke's law, because we don't always have this linear relationship. So this is a linear relationship. Notice here the graph curves downward. Here the graph curves upward. And here it looks like it's almost going to infinity. This slope is really, really large. Because you can imagine if instead of hanging this object on here, we hung an automobile or a tank or a battleship, then certainly these would have broke in all cases. Or what's probably most likely to happen is that it would disconnect either here or here. But if we had really good connections, then this object here would just snap, it would break. So that's not obeying Hooke's law, because we're exerting a very large force and then there is no stretch. So essentially the stretch goes to infinity. The delta L, as I mentioned before, goes to infinity. That's the generic relationship. It works with when forces are parallel or anti-parallel to the object in question. So oops, not parallel. But we don't always have forces that are just parallel to the object in question. Here's another example. So in this case, the force is perpendicular to the object. And note when it's perpendicular to the object, we're going to get this sort of bending here. I don't know if bent is the proper term here. My vocabulary is not that great. And we've got a certain length here. Where we apply the force is going to govern how much the object is deformed. So in this case, so actually let's quickly go back here. In this case, it wouldn't have really mattered whether we applied the force in the middle or right here. The assumption is that the cross-sectional area is fairly small compared to the length. It would make a tiny difference if we had a super sensitive instrument. If we apply the force here or here, but for the most part, the assumption for this tension and compression is it doesn't matter where the force is applied. But here, it does matter where the force is applied. So if we apply a force lower, if the same force was applied down here, the deformation would not be as great. So it's important to note that L0 represents where the force is applied. I'm going to circle that. So other than that, the form of the equation is pretty much the same. So we've got some sort of a deformation. We've got some sort of force over area. And we've got some sort of a constant. So we can rearrange this formula a little bit. Let's write it over here. Delta x equals 1 over s. F over a times L0. So let's multiply both sides by s and divide both sides by L0. So s delta x over L0 equals F over A. F over A can be called stress. And those of you who are familiar with a little bit of physics, this formula here Note this is also the formula for pressure. And it's measured in, obviously, force units, so newtons per square meter, for example. This delta x over L0 can be called strain. So this tells us that stress is proportional to strain. And just like always, we can change a proportion into an equality by including some sort of a constant. So stress equals some constant times strain. So in a generic sense here, stress is how much pressure exerted. So on the object, and strain is how much the object reacts. And obviously, not all objects are going to react the same. And the amount that they react is related to this constant right here called the shear modulus. So S is called the shear modulus. And it's interesting that Young's modulus, which is how much something reacts under pressure, being stretched or being compressed or stretched out, doesn't necessarily correspond hand in hand with the shear modulus, how much it bends, basically. And bending works well with a rod. Envisioning that, I don't know if you can say a bookcase like this bends, but my vocabulary is not very good, so I kind of think of it all as bending. But if we just look at the first two on the list, aluminum has a higher Young's modulus than bone, but bone has a higher shear modulus than aluminum. So that means that bone compresses easier. So if we just look at these two, or stretches, easier than aluminum. But aluminum is a lot easier to bend. So you can't just say, okay, this has a larger Young's modulus, so it's obviously going to have a larger shear modulus as well. There are other characteristics that shear modulus as a number doesn't completely describe. For example, you can imagine that bone is more difficult to bend, but once you bend it, it most likely is going to break. Whereas aluminum, you bend aluminum, you've got aluminum wires probably in your house, and you can bend those as much as you want. Not endlessly, of course, but you could bend an aluminum wire dozens and dozens of times in succession, and it's not going to break. Whereas the bone, you bend it past a certain point, and it just breaks. So let's work on an example here. So you're using a basic pencil eraser. So you've got your wooden pencil here. So I'm holding one up in front of the camera. And let's just say you exert a vertical force 6 newtons at a distance 2 centimeters from the hardwood eraser joint. So you notice on here, and you've looked at a pencil, the eraser and the wood meet. Now most pencils have this little metal part as well, but the eraser is actually attached to the metal part. There's little indentations on there, and it's touching the wood. Some erasers might actually be glued to the wood. I think for the most part, that piece of metal just kind of crimps them in. So this could represent an eraser attachment that isn't very common, but anyway, it's on here. And we want to know by how much does the wood flex perpendicular to its length, and how much is it compressed lengthwise. Right, so here's our pencil. And a lot of times these erasers are kind of a brownish color, so I'm going to add a color to this. Introduce kind of an ugly color to our palette. And then we're erasing on the table like this. Okay, so it's held at an angle of 20 degrees to the horizontal, so I didn't draw that angle very well. So theta equals 20 degrees. You're exerting a 6 Newton force, a vertical force, so that means that F equals 6.00 newtons down. And it's at a distance two centimeters away, so L0 equals 2 centimeters. So we're going to say that that is 0.02 meters, and the pencil is 6 millimeters in diameter. So A equals pi r squared, so that's equal to pi times 6 millimeters in diameter, so that's 3 times 10 to the minus third meters squared, and that comes out to be 2.83 times 10 to the minus fifth. Square meters. Okay, so how much does the wood flex perpendicular to its length? So we can break this down into components. So this is F perpendicular. So F perpendicular, if we go back here, so this is a force that is perpendicular to its length. So we're going to be using the shear deformation for that one. And notice that here's a force that is parallel to the length. It's actually better represented by this one. So it's parallel to the length. So then we're going to be using compression or Young's modulus when we do the mathematics. So this is a shear force. We're going to use the shear modulus. Then we're going to have a force that is parallel to the length. So F parallel, that's a compression force. And here we're going to use Young's modulus. All right, let's see if I have everything here. Oh, so we can actually look it up. Oh, so I cut off part of the list here because I didn't want to make it microscopic. So we'll just go with what I've looked up elsewhere. So S equals 1 times 10 to the 10th newtons per meter squared. And Young's modulus is 1.50 times 10 to the 10th newtons per meter squared. Okay, so these force application problems are typically pretty straightforward. Really just deciding, the most difficult part of the problem, I think, is deciding, is it a shear force or is it a compression force? So in general, the stress is proportional to the strain. So the stress is, the force that we're exerting. So this is the stress, and then the strain is how it's affected. So delta x here is going to equal 1 over s times the perpendicular force over A times L0. So if we plug those numbers in, I'm not going to bother to do that. We get to, if we carefully keep all of our digits here, we get 3.99 times 10 to the minus, oops, 10 to the minus, wait, did I read that wrong? 10 to the minus 7th, sorry. Thought that seemed pretty big. So that is a very small number. That actually is, so wood does not bend that much with that tiny, tiny force. In fact, this is roughly equal to the wavelength of light. So the pencil bends, it's deformed in that direction, so a shear force by a super tiny number, a number that's roughly equivalent to the wavelength of blue light. All right, so we're going to have, oops, so that is, so now we're using the compression force, and the compression force deals with delta L. So it's pretty much the same thing. The same format. So a change in some length parameter equals, this time, a constant. The pressure times L0. We plug in the numbers here. We get an even smaller number, which sort of makes sense. 10 to the minus 8th meters. So this deformation is about more than 20 times as much as this one. And that kind of makes sense because you can exert a pretty big force and bend a pencil noticeably. So in front of the camera here, I can bend the pencil a little bit. And I don't want to bend it too much because I'll break it, but you can see my hands moving down. But there's no way that you could detect any sort of a shrinking in the pencil along the length of it. So far we've just been dealing with motion in one direction, either squishing something or bending something. But we know that there can also be changes in multiple directions. So if we have something, a three-dimensional object, and we're either crushing that three-dimensional object or that three-dimensional object is growing, it is going to change its volume. So we can actually apply the tension or compression in more than one direction. So it'll respond just like that same tension or compression in one direction or one dimension. So again, notice the parallel nature here. Before we had delta L equals 1 over some constant F over A L0. So the exact same setup. So we have an initial, in this case, we have an initial volume, and we're exerting some pressure on that volume, and that volume is going to change based on the material property. Or we're not compressing it, that object is expanding, and it's going to exert pressure on its surroundings based on this constant right here. That constant is called the bulk modulus. And if we just compare a few items on here, so we look at those three. Cast iron has the largest Young's modulus and the largest bulk modulus. Marble is number 2 on both lists, and lead is number 3 on both lists. So that sort of goes in order. But the relative proportion changes a little bit, because for Young's modulus, iron is about, that's 8 times or so more difficult to compress or stretch than lead, so a factor of 8. But in terms of bulk modulus, squishing it like you would wring out a sponge, it's only about a factor of 2 difference. Same sort of thing here. There is a difference of about a factor of 4 between these two, and there's a factor of about maybe 50% between these two. Here's another one where steel compared to cast iron, a factor of 2 difference here, less than a factor of 2 difference here. So you can't, you maybe could say, well, there's some sort of pattern, like between cast iron and lead, that was a factor of 8 for Young's modulus and a factor of 2 for bulk modulus. Well, maybe because it's 3 dimensions and 2 to the 3rd power is 8. That has a little bit to do with it, but that pattern doesn't hold true here. It's not a strong relationship. So there's some other things going on as well. So the one thing you definitely can take from this is, in the vast majority of cases, the order of Young's modulus is going to be the same as the order of the bulk modulus. And the bulk modulus values are going to be closer together than the Young's modulus values. So let's work out a basic problem here. And you've encountered this before. When water freezes, its volume increases. So some of you have filled up a water bottle because maybe you're going to go bike riding, you're going to go hiking, and it's really hot. So you want something that's super cold because you know within an hour it's going to be all melted. So you fill up the bottle, or the first time, you kind of absent-mindedly fill up the bottle of water, and then you put it in the freezer. So what happens? The bottle of water will probably, certainly it'll squish out, because oftentimes bottles have those indentation at the bottom. That indentation will puff out, and depending on how full it is and how big that indentation is, actually the bottle could burst in your freezer. That's because volume expands of water. And that's actually a good thing for life, because that means that in the wintertime in a lake, the top of the lake freezes because the cold water is less dense. The ice is less dense than the liquid water, so it floats to the top, which leaves the bottom of the lake available for living things to remain there. If liquid water was less dense, then the ice would sink to the bottom. The living things couldn't live on the bottom. The top of the water would be cold because it's more exposed to the environment, and items would die off. So anyway, what force per unit area is water capable of exerting on a container when it freezes? And so you can use the bulk modulus. Look at that sort of, oh, it is acceptable to use the bulk modulus of water for this problem. Kind of presumptuous there. We are going to use it. Okay, so we want to know what pressure so pressure equals force over area. So we had delta V equals 1 over B force per unit area times V0. So F over A equals B times delta V over V0. So this one's pretty straightforward. The bulk modulus for water, and I forget if I have cut that out. So these are in alphabetical order. Yeah, I forgot. So that one is not here, but never fear. We could just look that up, and it turns out that the bulk modulus for water is 2.2 times 10 to the 9th. Newtons per meter squared, and delta V over V0 is 9.05 times 10 to the negative 2. And notice there are no units here because it's delta V divided by V0. So they would have the same units, meaning the end result is dimensionless. So if we plug all that stuff in, we come up with two times 10 to the 8th newtons per meter. That's a huge number. Let's get that into something, square meter. So that would be 2 times 10 to the 4th newtons per square centimeter. That would be about 4,400 pounds per square centimeter. And for our American and Liberian friends who don't use the metric system, that's about 28,000 pounds per square inch. And air pressure is about 14 pounds per square inch. So this is 2,000 times the amount of air pressure. So 28,000 pounds per square inch. A typical car is maybe 3,000 pounds. So 3,000 pounds, this would be about 8 cars per square inch. And your thumb, different people are different sizes, but your thumb, that last bone in your thumb, or maybe your entire thumb if you're a smaller person, that's about 1 square inch. So when water freezes, it's pushing out on your water bottle with a pressure equivalent to about setting 8 cars on top of your thumb. So when you put that water bottle in there and it bursts and you sort of curse the water bottle, you curse whatever company produced that, and you say, ah, stupid company, stupid Coca-Cola company, their bottles are so weak. Well, next time you say that, remind yourself, oh, you know what? That's like putting 8 cars on my thumb. Maybe that bottle isn't so weak. Maybe there's just a lot of pressure exerted by expanding objects. So that is the fact of the day. Water, as it expands, exerts about the same pressure as stacking 8 cars up on your thumb, or something else at a square inch, roughly a postage stamp. Stamps come in different sizes, of course, but a postage stamp is about that same size. As I said before, let's just kind of review. Note the similar format in these formulas. Delta L equals some constant times pressure times the initial length. That's really just a specific application of this thing called Hooke's law. So anytime there's a proportionality between how much force is exerted and how much that object deforms, that object obeys Hooke's law. Sometimes that force is perpendicular to the object. The relationship is still the same. All the dependencies are the same. It just uses a different constant. Just because something is difficult to compress compared to another object doesn't mean it's difficult to bend or shear compared to another object. So aluminum and bone are a good example of that. Here's an example, just in everyday life, you're pushing down on your pencil to erase something. You are barely compressing. You're barely bending the pencil, and you're barely compressing the pencil, not even a measurable amount. You probably use way more than this much eraser is crumbling off. So if you say, oh, I feel the pencil getting shorter, that's because the eraser is crumbling off. Or if it's sort of a soft eraser, the eraser is squishing. The same sort of thing happens in 3 dimensions as well. Think of a pop can or a water bottle put in your freezer. And that pop can or water bottle put in your freezer, because pop is basically mostly water, exerts a huge amount of pressure. Thanks, and we'll talk to you later.